Welcome everyone to the July 2026 meeting of the Mornington Peninsula Astronomical Society, and I think I'll begin first of all with the bad news here. What you're seeing there is Earendel 1, which is going to be launched in the next couple of months. The Federal Communications Commission in the USA has approved the company called Reflect Orbital to start putting up their 18-metre wide sunlight reflectors into low Earth orbit. There's only going to be 2 this year, but it's going to be ramping up significantly up to 50,000 by 2035. So you're going to have 50,000 in low Earth orbit of 18-metre mirrors. And why you'd actually have these is if you've got someone that's willing to pay for reflecting sunlight down to the Earth's surface, they'll basically swing the low Earth orbit satellites round and point the sunlight at the Earth. Because they're in low Earth orbit, they'll only be reflecting the light for a short period of time, and then another satellite will have to come in behind it to orient itself to the correct angle to shine it at the Earth so that you have constant illumination on the ground. Now, each one of these satellites is going to provide the equivalent illumination on the ground of 4 full moons at the time, and there's going to be 50,000 of them. And they're promising that they'll make a schedule list available to professional observatories so that they could find a spot where there's not going to be anything over them at any one time, which I'm sure is going to go down like a lead weight. So that approval came through as either today or yesterday USA time. So they've been given the nod on that one, despite a lot of objections to it as well, as you can imagine, for people that want the night sky. The other thing to note is over on the right-hand side there, the animation there. This is of using data from the Hubble Space Telescope going back 20 years, and more recently from the James Webb Space Telescope looking at Omega Centauri. And what they found in Omega Centauri is they've finally identified a black hole inside Omega Centauri that's about 4.5 times the mass of the Sun. So it's a relatively small black hole. But not small that it's the result of one supernova explosion. It's obviously something that has either had a merger of black holes occur to make it larger, or it came from a particularly large black hole. And they reckon, based on the frequency of supernova explosions, something the size of Omega Centauri in the sky, and for those who are unaware, it's sort of over there where the Southern Cross is, that they anticipate there should be about 10,000 of these black holes just in Omega Centauri alone. Now, a couple of years ago, they found a very large supernova right in the centre of Omega Centauri via a different technique, and that one was several thousand solar masses, so far too large to have been a single star coming to the end of its life and blowing up and forming a black hole. So it's thought that for that reason, as soon as they found that supergiant black hole in the middle, that they realised that Omega Centauri is a dwarf galaxy that has been cannibalised by the Milky Way and basically been stripped of the stars around it. So what you're seeing is the core of what used to be another galaxy if you go back a while when you look at Omega Centauri, because there's no way that you can actually get a supergiant black hole in the centre of a cluster of stars of the size of Omega Centauri on its own. So what you're seeing there is what they've managed to measure in its orbit. So they measured about half of one orbit over the time of the Hubble Space Telescope. Now, the other thing to note was the Chinese, hot on the heels of the USA's effort, have gone sort of one up in their reuse of rockets. So this shown here is their Long March 10B rocket, and this is reusing it after reusing the first stage of the rocket after it's put something up into orbit. At this stage, I don't think it was putting something up into orbit, it was a test. It doesn't have any landing gear on it at all, so it doesn't have any feet like Elon Musk's. It's actually caught in wires, and you see this wire cage it's actually landing into here. It's got cross wires across it, sort of going across like that and cross like that. And with a bit of clever engineering and some very careful aiming of the thing as it's coming down, they catch the rocket. And it basically ends up suspended above the ground, so it doesn't actually touch the deck. Given that it's got this massive structure on the top there, I think the barge has to be a little bit larger than the ones that, say, SpaceX uses. But it doesn't have the same issues that SpaceX does. Now, if you remember when SpaceX ones come down, they fire explosive bolts on the feet to actually weld it to the deck of the barge, and that's how they stop the thing from tilting over in the movement of the ocean. And if I go on to the next one, oh, this one's got a bit of audio in it. You'll see how the wire works. Notice how the cross wires quickly close up in two dimensions. So even if the rocket is a little bit off, they will adjust themselves to match the rocket. So very, very clever innovation building on reusing that. Speaking of the Chinese, the one down the bottom there, this is one of Earth's other moons. We have obviously the big moon in the sky that everyone's familiar with, but we also have a few smaller moons in orbit around the Earth. They're in unstable orbits, so they're probably only going to be hanging around for millions of years before they'll come crashing back to Earth. And this particular one here, the Chinese Tianwen craft, got to within 20 kilometres of it and took this photograph. The size of it is about 20 kilometres itself across, so it's quite a decent sized rock, about twice the size of the one, or twice the diameter of the ones that wiped out the dinosaurs. So it's significantly bigger, given that it's in 3 dimensions. And their probe is going to go into orbit around it for about 9 months, having a good close look at it, and then it's going to attempt a landing and bring a sample back to Earth. Now, what they think with this this one that was detected by the observatory on Hawaii, and hence why it's given this Hawaiian name down the bottom there. Don't ask me to pronounce that Hawaiian name. That's the name of the asteroid around Earth. It got there on the 2nd of July to within 20 kilometres, and now it will slowly do a bit of reconnaissance of it before landing and bringing a sample back. It's thought, but they're not sure, it's thought that this is ejected from the moon. So in other words, some past impact has thrown a large lump of the moon into space, and it's now come close enough to Earth. It's still quite away from Earth. It's still, I think, about 0.8 of an AU away from Earth, but it is in orbit around the Earth. And you don't want something that size, 20 kilometres across, colliding with the Earth, otherwise you're looking at a dinosaur level extinction, or a lot worse than that. So it will be very interesting to see over the next year or two whether the Chinese are able to pull it off and bring the sample back to Earth, and then that sample, whether or not it's able to be shown to come from the moon, or indeed whether this was just an asteroid from further out that came too close to Earth's gravity and got captured. Now, it's thought even if they successfully work out what it is, because it's in an unstable orbit, they say it's going to crash to Earth sometime in the next 100 million years anyway. So it's not going to stay up there forever. So it'd be a good one for some target practice once you're confident of what's going to happen to it when you do try and blow it up or push it out the way. Because 20 kilometres sounds a lot. It's the size of a mountain, but it's tiny compared to a lot of the asteroids out there. All right, tonight, welcome everybody, and welcome to the new members here. And we have one new member since last meeting, Anthony Xalis. So welcome, Anthony. I don't think you're here tonight, but welcome to the Society. And feel free to come up and say hello to anyone on the committee when you do come along to one of our meetings. As usual, I'll talk about events past month and coming month. There won't be an Astromofo today from Chris, so I don't know if you wanted to say anything about the APW at all, Chris? No? Okay, fine. Yep. So Chris isn't here. He's sitting quietly in the back there. Then I'll throw over to Guido for Sky for the Month. Then we'll look at decoding the universe through spectroscopy via the Professor Raghunathan Srianand from the Inter-University Centre for Astronomy and Astrophysics in India, which is a very interesting collaboration there. I'll explain a little bit more a little bit later. Then we'll look at why does light actually bend when it enters glass. In high school, the students are taught the rules of Snell's law and so forth about how refraction occurs when light goes into glass or water or any other similar medium, but this explains why it actually occurs, and it debunks some of the whys that are taught as not being correct. Then we'll look at collisions of neutron stars via this latest NASA supercomputer simulation from a couple of months ago. Now, recent events. Oh, we've had lots of recent events in the last month since we last met. 18th of June, we had the first and second Mornington Scouts here at the Briars, and they had a really good clear night on that night. Then the next night we had the winter solstice people from an Echo Centre next door came over for a bit of a view through telescopes, and I also gave them a bit of a talk about Earth and solstices as well while they were here. 20th of June, the next day, we had the Working Bee and the Members Barbecue, and the Monday, the 22nd of June and 23rd of June, we had two groups from Patterson Lakes Primary School. We had all of their year kindergarten to year 6, so virtually the whole kindergarten came, the whole primary school came along. The first night got not too much cloud, and the second night unfortunately was overly clouded, and that's why more people turned up, because it was totally clouded, and, of course. 24th of June, so the very next night, we had a whole host of scouts. I don't know what the collective noun of a group of scout groups are, but we had Red Hill, Balnarring, Mornington, Dramana and Mount Eliza Scouts. I don't think it's called a jamboree, but it would be some other sort of collective noun here at the Briars, and we had the place pretty much full on that night with scouts, and fortunately they got to see something. Committee meeting on Zoom, we had the emergency management plan finalised thanks to the effort of Ali Midwood and sort of facilitated by Phil Peters as well. And for those of you who want some good bedtime reading before you go home, here's the emergency management plan that Ali has kindly printed out for us. We also talked about the website refresh, the annual general meeting preparation, the Cosmology Day, and also looking at the new area of the site down the bottom on the other side of the current fence, which will be undergoing some changes in the coming year for sure. 3rd of July we had the public night here where Guido gave the talk, and we had only a little bit of cloud there, so that was quite good. It was quite a cold night. 6th of July we had the International Olympiad students here. These are the year 11 and 12, and they asked some pretty hair-raising questions, and they were lucky enough to get no cloud at all that night, so they had plenty of chance outside to manually find things in the sky, and it was quite illuminating to find how many members here couldn't read a star map and turn the telescope around manually to find something in the sky. So something we might have to work on. And then on the 11th of July, just a few days ago, we had the Cosmology Discovery Group here, and they had 27 members turn up for that one. Coming up, we still have quite a few events in the following month. This Saturday we've got the Working Bee, a members barbecue from 4 p.m. here at the Briars. On the Monday and the Tuesday we've got Toorak College Girls Grammar coming with in 2 busloads on the 2 nights. All of them are year 7s, and we've done this school several times now over the years. 22nd of July will be the committee meeting. 24th of July on the Friday we've got the usual SCAG meeting, Scout Cubs and Guides, and we do have some book for that, so that one's definitely going ahead. And 6th of August, there's a little bit of a gap there. 6th of August we've got Balcombe Grammar from just up the road here coming down to the Briars, and they'll be sending their year 10s down for a night here. The next day we got the public stargazing at the Briars, where Manfred's on the hook for the talk there, and he's fully booked out with 100 people booked in, so the place will be buzzing. The week after was the Indigenous Astronomy Public Night. We moved that 7 days earlier to get Tim Paxton's availability here, and we've still got plenty of tickets available for that one. Members can attend these for free, by the way, when you go to the Indigenous Astronomy Night here at the Briars. 17th of August, we've got Strathcona Girls Grammar. Now, we've done this school several times over the years, usually at different camps around the peninsula. And this time they're going to be right next door to us, so that's nice and pleasant. And so we'll have the Year 10s come into that for those girls. The next night we've got two things going on the same day. We've got Trevor going down to Rosebud to speak at the library, and that evening at 6:30 we're going to be at the Scout Hall of Baden-Powell Park Scouts, which is on the border, I think, between Mount Eliza and Frankston South. So we've been there several times over the years as well. So there's quite a few of those 70 Scouts. Monthly society meeting at the Briars the next night, and then the very next night after this meeting next month, we're going to be out at Croydon for Ainsley Parkland Primary School. And we're expecting 100 students there, so we're going to need plenty of telescopes out there on that particular night. And on that exact night as well, and at exactly the same time, Trevor will be going down to Mornington Library to give them a talk. So we've got 2 nights and 2 events going on at the same time. So a busy time.
So I'm finally back in Australia and can do Sky for the Month in person, which is nice. So this is for the rest of July and the first half of August. The first thing we're going to look at is the solar system from above, basically. I played around a bit and found a new visualization for this one, and it's also going to be on our homepage. And I think it's a bit clearer than the other one, because now we actually have all of the planets on here at the same time. Let me just quickly try and find a laser pointer. So we've got the sun in the middle, and then like all of the planets. The actual orbits are a bit, we probably have to turn the lights down a bit to see the other orbits. But yeah, you can see Earth is around here, so we're just past, just past the winter solstice, which would be right below the sun actually on this point. Thank you. All right, and in this view, you can actually see that anything on this side here is in the evening sky, anything around here is in the morning sky. And so we can have a look at that over the next month or so. So this is for tonight, for the 15th of July. You can see the little moon there just above the Earth. So we're just past the new moon, actually. Let me see whether this will play. Yep, okay, so this is now over the next month how the planets are going to move. So you can see Mercury now reappearing from between the sun and us, and Venus is in a very nice position to view at the moment. So that's a very bright evening star right now. And then in the evening sky you can see Saturn and Neptune, quite nice to observe. So a lot earlier now than a few months ago, but Jupiter is basically hiding behind the sun from our position. There's also an alternative view if you kind of stuck in the, I don't know, 16th or 15th century. So this is the geocentric view, where we have the Earth in the middle, but it's actually quite nice because it's a bit clearer what's actually in the sky and where. So we can do the same thing here and look at that over the next month, where we can also see like the moon there circling around us. And you can see that Jupiter is basically, I mean, here it looks like it's between the sun and us, but obviously it's just hiding behind the sun at the moment. All right, I'll show you a bit later. We've got this now on the website as well, so you can basically check where the planets are at any point. All right, so let's have a look at the night sky on the 1st of August. So we'll have sunset, I think around 5:30 or so. You can already see there Jupiter just hiding close to the sun there, and Venus very high in the sky, so nice bright evening star. And Venus will be at greatest elongation east on the 15th of August, so in like 1 month from now. And Jupiter will have its conjunction with the sun, so exactly behind the sun from our point of view, on the 29th of July. The moon, you can see right there just above the horizon in the east. We've just had the new moon yesterday. The next full moon will be on the 30th of this month, and then the new moon in August on the 13th, and then again on the 28th, the full moon in August. Right, so going fast forward to around 10 p.m. and then having a look at the brightest stars in the sky. So we can now just at the top there see, I have to look at my screen here, otherwise I can't point. These 3 stars here, that's the northern hemisphere summer triangle. So that's just about coming into view for us now around 10 p.m. with basically Vega and Altair at least quite visible around 10 p.m. And then the other, well, you can see Canopus here now almost setting already at 10 p.m. And the other 3 bright stars around here will be much higher in the sky than they were a month ago. So Altair, Fomalhaut, and Acana there. If you look straight south, the Southern Cross is now around here. It's a bit lower than last month, and everything here is well past the meridian at 10 p.m. now, whereas previously it was closer to the meridian. All right, let's have a look at the constellations. I think I'll skip that one. But I mean, we have Sagittarius and Scorpius. They're kind of almost straight above us at 10 p.m. Okay, continuing on. Neptune rising around 10 p.m. and Saturn not that much later, 10:45 or so. So we will get those planets, at least in particular Saturn, back for like comfortable viewing times in the next couple of months. And then Uranus 3 a.m. and Mars a little bit later at 4:30. And then I think we'll have the sunrise at, Mercury is a morning object at the moment. It will be at its greatest elongation west, so the furthest away from the sun in the morning on the 2nd of August, but it'll stay pretty close to the sun, so not really observable. Sunrise around 7:17 a.m. on the 1st of August. The apparent sizes of the planets, not that interesting because Jupiter is just not visible at all at the moment, but Saturn is getting a bit bigger, and we're also heading towards the opposition of Neptune in the next few months. I found one conjunction on the 16th of August where the Moon and Venus will be within 2 degrees of each other in the evening sky. So that's around 6:30 or so. So that could be quite nice. Comets, I found one comet that's maybe brighter than 10th magnitude. That's 10P Tempel 2, but apparently it'll fade quite quickly from now, so probably nothing really that interesting at the moment to observe. And I put the same 2 meteor showers on here that I had on there last month. So the Southern Delta Aquarids and the Alpha Capricornis, so both of them peaking around the end of July. But that's exactly when we'll have the full moon, so that's about the worst time you could observe them. So unfortunately, both of those won't be that interesting. Right, and then to finish off, I just wanted to quickly show you parts of the new website. And let me see how this will work. There we are. So that's our website, and I literally just before this presentation finished this, where when you go to members and then click on Sky for the month, you now always get the latest article, the ones that Nerida writes for the Morning Peninsula magazine. But I added a few extra features to the article. So you've got the nice cover image and so on. But I added a few highlights, like in terms of conjunctions, or when I don't know, planets go from retrograde to their normal motion, those sort of things, and the meteor showers in there. Then we've got the article, and then things like sunrise, sunset, where the planets are at the moment, whether they're visible or not, the moon phases, meteor showers, and then the solar system view that we saw earlier. So that'll be a nice resource whenever you want to just figure out what's in the sky at the moment. You can just basically click on that link. And if you want to know what's in the sky next month, we don't have the article up yet, but all the other information will be there. So that'll get basically added every month as we go with the nice photos and the article. And I think that was all. I can't find my presentation again. But just finishing with the sources that I used, as always, were NASA Eyes on the Solar System, this time more as an inspiration for the new tools, and the Astronomy Yearbook, and the Comet page that I can really recommend for everybody, and we'll put a link somewhere up as well. And yeah, that's all from me.
So tonight's feature is all about spectroscopy, decoding our universe, and shown here is Professor Raghunathan Srianand, the Director of the Inter-University Centre for Astronomy and Astrophysics in Pune in India, so sort of in the Midwest of India, if anyone's wondering where that is. He's a cosmologist and astrophysicist, and this public lecture was given in 2024, and courtesy of the IUCAA, which is up above. Those of you, I've included the link to it at the bottom there, because at the end of it, and I don't include it here, they had a demonstration of how to make a spectroscope using an old CD or an old DVD and a matchbox. The only reason I didn't include it is the audio on it was so bad and I couldn't fix it, even with AI. So you might be able to look at it and actually figure out what they're doing, but combined with the quality of their microphones and the softness of their speaking, it would have been impossible to actually show here.
So nice to see you all here. It's a full house, so that always makes us happy. So I'm Samir Duide from IUCAA, the Inter-University Center for Astronomy and Astrophysics, and I welcome you to the first lecture in this every yearly series of second Saturday lectures and demonstrations also. Okay, so we are here. We've been doing this series for more than 30 years now, and every year we get a lot of prominent scientists, people who do research, people who study science, and they have methodology, they have way of doing research, and they research various aspects of nature. And what you learn in school is someday, hopefully, also going to be something which leads you to do this kind of research as well. So to give you a first hint, first glimpse of a scientist's mind, a scientist's work, we bring them to you on this platform through this series called the Second Saturday Lectures. So that's a background for that. And we also have other outreach winners, which I will announce to you at the age of the pen. But we are even waiting for the first talk today, which is to be given by Professor Srianand. And he's an Indian astronomer, astrophysicist, cosmologist, who's been in this field for many years. Since the beginning of IUCAA, he's been with it, and he has studied things which are close by him, like scholars, like devices, something of the universe. Today he's here to explain to us in simple words a method that he uses for finding out more details about these famous galaxies, and then the method which is in general also used by many scientists in many other fields. So that was a very becoming our unit. So like this step, you just now looking to Srianand. Thank you.
Good morning. So today I'm going to switch off this. Okay. Today I'm going to discuss what is known as astronomical spectroscopy. I understand that you are out in school, so you would not have done any physics. So I would like to explain to you in a simple way. The idea behind all these exercises is that when you look at the sky, you see these objects, right? Night sky, you see stars and whatnot. And if you look at the pictures taken by telescopes, you find interesting features in the sky. Unfortunately, we cannot go over and touch and see. See, never again, and if I give it stone to you, we can touch it and we can make it and see what is inside and out. In astrophysics, and we can see mother. Okay, it took so much time for Chandrayaan to reach, or I could to reach Moon, which is the nearest object. It took how many days it took? Younger? So many days, no? It was just going several months before reaching there. So it is impossible for us to go to any astrophysical object and look at it and try to see what is there, why it is like this, what can we say about it, okay? So astronomy was based on these methods by which you sit here, you don't go there, okay? You don't go there, you don't touch or do something. By doing some special experiments, we are able to understand various things about our universe itself. So I'm going to just walk you through simple ideas of what is spectroscopy. You see them every day. So to understand basic ideas, then I will develop. So I'm assuming that you will be able to follow what I'm saying. In case you see that I'm saying something which is slightly goofing up ahead, just tell you so that I can give you explanation which is much simpler. Okay. Spectroscopy is very simple. The first idea to see that any light which we see here or sun or something, they look like white color. But we know that the white color doesn't mean that all, if you on the light which is coming from there has only one color. Actually, mixture of all colors together will make a light look like white. Okay. Is it true or not? So we have seen the example. The example is you see in real life a rainbow. Okay. You have seen the rainbow. Rainbow, you see this color, whatever, violet to red. And you need the orientation where how it has to be. Some rain should be there, some cloud should be there, sun should be behind. Sun is behind. When you look at in the evening or in the morning, when there is going to be rain, you will find the rainbow. So when you start with sunlight, sunlight has all the things together. Everything is mixed up. This light enters into a droplet. So is it one of the things you will learn in optics when you see how the light goes through something. When a light goes from some air into a glass, it will not go straight. It will turn. Okay, this bending will happen. So, and interesting thing is that not all the light will bend by the same way. The blue color light will bend slightly less compared to the red color light. Okay, because of this, what happened when you are entering here? Everything is coming together. When you enter here, one will bend more compared to the other. Okay, and what happened? This light will go and reflect again, and it will come out of this drop, water drop. There is a water drop. You are going from here. You enter into the water drop. You are going from something which is less into something which is big. Actually, you can see this. If you go to swimming pool, you put a ball in some place, it will appear as if it is displaced like this. You have seen this? The swimming pool mein सीधा नहीं दिखता है कुछ भी, right? It depends on, and in fact, you can make an experiment. You can take different color balls. You will find that they will appear displaced little differently. This is the idea here. Okay. So other way of saying is that suppose imagine we have made this. You are all going to a cricket match or you are going to cinema hall. What they have done is that just to mediate the crowd, they have constructed small gates. Okay. Then what happened? The gate which is narrower, only thin people will go through. The gate which is broader, only bigger people, everybody can go, but preferentially bigger people will go. So if you ask the whole crowd to go, and if you keep this kind of entrance there, and you will clearly see the segregation of people. So the thinner people will be in one side, bigger people will be in the other side. Okay, so this is the kind of thing
light can do when light goes through a simple medium into a thick medium. Thick medium can be water, thick medium can be mirror. So this is what you see examples. It could be oil also. This is the example you see in the road. Na? Have you seen in the road when you, in a rainy day, when you go, you will see these colors in some part of the road. Do you understand what it is? It is basically, it happens because there is a thin layer of water or oil spread in the surface. The same thing happened to the light which is coming from outside. When it's entered the oil, blue color and red color will deviate differently. It cannot go through the road, so it will come back to you. When it comes back, it will come at different angles. So it will appear as if you have different colors. So now the question again you have to ask, whether the colors are produced by oil or colors are nothing but the light which is being deviated into different colors by this oil. How do you check? You just go with the same place where you are seeing this oil spill. If you cover yourself with a blanket completely and see, you will not see any light. Any color will not be there. These are the experiments you can do in your house. The same thing you will see if you go to garden and if they do the sprinklers going around. You can see every time. So again, this is the example here. If you have a sprinkler going here and you stay behind, your son is behind, sprinkler is going here, you will see nice pattern. You ask your friend to see in the other, stand in the other side, he or she will not see this pattern, whereas you will see at a particular angle. So clearly what I am trying to say is that all the colors and other things we are seeing in this kind of thing is nothing but we are seeing the light from sun only. Okay, we are not seeing it from anything else. This water is not producing light. Water cannot produce light. So this is the first idea. The first idea is that any light you can think of can be spread into light as a function of color. This color in physics goes by the name wavelength. Okay, we will keep calling it as lambda or whatever. Wavelength is what we need to know. So you understand, any object you look in the sky can be split. That light coming from that object can be split into these colors. Okay, good. So this is what it is, but actually the light covers huge range. It is not only the range what we are seeing. So you know that you have X-rays, you go and take X-rays, na? Like that in sky also there are X-rays, right? You can also have radio, we are listening to radio. So the object in the sky can emit light or emit signals in any wavelength, okay, any region. It can emit signal in radio, that's why GMRT is there. You heard about GMRT? GMRT is there to detect the signal like what we hear from radio, okay. So this is the idea here. The first thing you have to remember is that any light, any signal coming from any object can be spread into wide range of color in place where we can see. It can be spread into wide range of frequencies like the way we tune our radio, okay. The frequency, wavelength and all are there. So that's the first thing to remember. The second thing to remember is, suppose this bulb is there. So I have a bulb. I just take a piece of, okay, you can take your mobile, okay. Go close to the bulb and take a picture. So mobile pura, it will be fully kind of this thing. You can imagine this is your mobile phone's photo. You keep moving out, the object, that light will become dimmer and dimmer and dimmer and dimmer. You understand why? Because basically what happens, if I am here, anything I send, I will send in all directions. Suppose if I have 100 people, I am going to send 100 people in all directions. So if you come and cover them with this, you will detect all 100, you can catch all the 100 people. So with this much circle, suppose imagine that I draw a circle from center, I send 10 people. If you are standing here, it is most likely that you will catch 2 or 3 people, okay. But if they are spread out, each one of them run 100 meters and I try to catch, it is most unlikely that I will catch any one of them because they have spread over a large distance. This is what happened to any light or any signal coming from an object. If you are very close, the object will appear bright. If the object is further away and further away, they will appear faint. This is the thing you have to understand also. The first thing we are saying is that any object you look at will be split into colors, right? That is just how they are spread in this thing. But how strong they are depends on how much closer these objects to us. Okay, this is another thing you have to just remember. These are all simple logic only. Now you are following whatever I am saying. So this is the problem for us. If you want to detect a distant object, it is going to be difficult, because more and more distance, the object will become fainter and fainter and fainter and fainter. Then it is going to be the. The third point, which I have not mentioned here, but it is also important for us, is that in this room there is no problem. I am speaking, you are immediately hearing. Suppose if I go and sit in sun and send a light pulse towards you, a signal to you, how much time it will take for that signal to reach you? Huh? Yeah, 6 or 8 minutes or second. So you see, it is very far. So if I go and simply switch off the sun, I go and switch off the sun, will you know immediately? No. No. So this is another point you have to remember. Objects which are near to us will be brighter, and we will know how it is recently, not even today, recently. The nearest star, it will take 1 or 2 years for light to come to us, okay, from nearest star. Nearest galaxy, it will take 1 followed by 8 zeros, that many years, okay. So you know, like, whatever we are seeing in the sky is too huge, it's too big, okay. Compared to any scale we can think of, these are very big. So 3 things we have learnt now. One is that any light will be split into colors. Second thing we learnt is that if the object is nearby, it will appear brighter. The same object will appear fainter when it is far away. So you look at an object, in our case we can easily say, na, if I give you 2 bulbs, one is faint and another is big, you will say that that bulb has a higher wattage here. But in astronomy it is very difficult to decide. If I find an object which is faint, you can say, okay, its energy is less because it is faint, or you have to say it may be bright but it is far away from us. So these 2 options are there, okay. The second thing is that when the object is far away, further the object is, it is going to take more time for you to decide what happened in that object. So you are actually seeing what happened in the past. So now I will introduce you. I am not going to go into, we will not do lot of details, but we will do simple things which we have done in our day-to-day life. So you would have seen this, people making a knife, or people making whatever this molds with iron. What they do, they heat the iron, okay. Iron will reach some 800, 600, 700 Kelvin temperature, and then they start beating it to get the shape. But when you look at it, you see something. The person is holding the rod here. That means that place cannot be very hot, correct? If it is very hot, you will die basically, right? 800 Kelvin you will not survive. 800 degrees centigrade you will not survive, okay? That's what it is. So clearly one thing which is clear, you look at this color is changing. It is very dark, pitch dark here. It's very bright here. So first thing is that we know this is hot and this is cold. So hot and cold will reflect itself in the form of colors, okay? How an object looks, it will be directly related to how hot it is, okay? So this in physics goes by the name blackbody radiation. So even if you don't know, it goes by the name blackbody radiation. The idea is very simple. When an object is extremely bright, it will appear in extremely hot, it will appear in a different color compared to when it is cold. In fact, it is counterintuitive. If I ask you to draw something very hot, you will plot something red, right? This is what we have been told, red hot. But actually the hottest is blue, extremely hot. In energy wise, if you see in physics, the object which like bluer and bluer will be much hotter compared to object which like redder and redder. So this is just our visual. So you can just to do this exercise, this what is done here is that, here what I am plotting is wavelength. Wavelength means lower wavelength means towards blue, higher wavelength means towards the red in color, okay. What is plotted here is the brightness, how bright, the y-axis here. So you have known this xy plots, you have done this distance versus velocity and things like that. So this side is wavelength and this side is, you can think of like brightness for our purpose. So if you take this curve, what it tells you is that if you are going below this wavelength, you will not see anything from this object. Starting from here, if you go, it will keep going up and there will be a peak and it will come down. This is predicted from basic physics. If you take a gas and gas it at some temperature, what will be the radiation it will come? It was predicted by Planck, okay. So you know this black body radiation. This is well known, and you will study, if you end up doing physics, you will derive these equations and study what happens and why it is coming and all. As far as we are concerned, we believe that these scientists have done a good job, and they have plotted this curve for different temperatures, only that much. So what do you see? This is plotted for 7000 Kelvin. This is plotted for 6000 Kelvin. You know what is Kelvin, na? Okay, good. So you can clearly see there, if I tell you, there are two things which is happening directly. One is that when the temperature is high, that if I ask you what is the area under this curve, how much area is covered by this curve, it is large compared to the area. Suppose if I just take all the things below this curve, this 7000 curve has lot more area. Okay. The first thing you are seeing is that higher the temperature, the area under the curve will be larger. Okay. Area under the curve is nothing but total energy. How much energy you receive from the object depends on the area under this curve. The first thing we notice is that when the temperature is larger, you will have more energy coming from this object. Second thing is that when the temperature is larger, the peak is towards lower wavelength. See, you take the peak here. It is here something like 4000 something, 400 nanometers. If it is 5000, the peak is somewhere here. If it is 7000, the peak is somewhere here. What is the meaning of peak? Peak means that is where the maximum light from this object is coming. Okay? So now if the object is very bright, that means it is very hot. Where the light comes, where the maximum energy is coming, you see maximum energy is coming from the bluer side compared to the redder side. So this is the first thing we learned. First thing we learned from simple thing is that if you take a star like this object, star is at some temperature, and if it is emitting radiation, and if you are going to look at it, what you will see will depend upon where the peak is. If the peak is at bluer side, this star will be very bright, and the star will produce lot of energy. Okay, and it will be at higher temperature. You are understanding? This, I am just giving you example. This example you have already seen. This is, you can have an object will emit in different light depending upon what is the temperature. You have seen, but you cannot compare these two because this is slightly different physics. I just gave an example for what to look at. Don't compare it with this. Why are we doing this? We are just doing it because this is the photograph of a region in sky where lots of stars are there. Are they looking same color? Some of them look yellowish, some of them look red here. If you look at it, some of them look blue. So what does it tell you? The stars don't have the same temperature. They have range of temperature. Okay. The first thing we learned is that stars have range of temperature. Okay. So let's see what else we can learn from this simple physics we have learned. So before going that, I wanted to say few things to you, so that we will set up our physics correct. Okay? This is one of the tricky thing. Afterwards, it will be just photos and we will go through. So first thing we learned is that you take a hot light, pass it through prism or whatever. This we have already seen. Any place where the light enters from low density to higher density and come back out, you will start creating these colors. So we have seen it. So this is what is known as continuous light. You remember, this is what you have to remember. Any light you see going from violet to red, it is continuously there. Color is changing continuously. So this is one kind of light you will see. That is the example is that when the object is hot, it will emit radiation in all wavelengths. This is called continuous. Continuous means all wavelengths you see them. Okay. The second set of things you will see is that in some cases you will see these kind of lines. Okay. I will show you examples. It is not continuous. Suddenly you see some lines appearing. So you will see the demonstration later on when you do after my talk. So what are these lines? Lines means what? There are photons, but they have only one wavelength. If you have photons with all wavelengths, some of them will be in blue, some of them will be in red. So it will be all mixed. Okay, it is like this thing now. If you say that, look at this room, I want to look at the distribution of heights of people. So chota log bhi honge, tall people will also be there, but there will be no difference. Now, continuously it will be there. But I put a box, again same experiment, I put a box. This box will allow only people with the height of 1 meter, people with exact height of 2 meter, and that's it, or 1.5, okay, 2 is too large, 150 centimeter or 100 centimeter, exactly you have to be there, okay? And you come in, now I ask you the distribution of people, you will have only two branches. One set of people who are only 100 centimeter high, another set of people who will have 150 centimeter high. Correct? You understand? When you take the distribution of heights of all of you, this is called continuous distribution. But I put some restriction. I say that only people who fit into my gate can go in. Who can fit in? Either 150 centimeter or 200 centimeter. If I put the distribution, you will find only two groups will be there. There will be nobody with 130 centimeter. There will be nobody with 80 centimeter. Okay? So this is what is known as line in spectroscopy. So how do you do this? How do you do this packing? Have you say you should be only at this height, like the way I said? How do you say? This happens if you want to understand little bit about atoms. Have you heard what are atoms? What are atoms? You have a nucleus and you have an electron. This is the smallest constituent of any of the objects we can think of at our scale. Of course, nucleus itself is not, meaning atom itself is not constituent. You will have further divisions there. So what do you understand? If you take a hydrogen atom, I will have a proton and an electron going around. Is that the picture you have learnt? Yes. But actual hydrogen atom is like our buildings, right? You know our 20-story buildings. The hydrogen atom is exactly like that. It is not like the picture you have to visualize is like this. So your house is the atom, you are the electron. So you can decide where you want to be. You can decide in the ground floor, you can go to the first floor, you can go to the second floor. Okay, fine. This is the experiment, don't do it. If you are in the first floor, you jump, what happened? You fall down, but why do you fracture your leg? You release some energy, right? Do you understand this way? No, no. You can take a stone, throw it down from there, you don't fall, throw a big stone. What happened? Wherever the stone falls, it will create a small crater. Why? Why? Because, second question you have to ask, how will I go from ground to the first floor? I have to do some work. Either I am fit, so I run to the top, or I am unfit, so I use electricity and go by the lift. So the idea, atoms are like that. Okay? If you want an electron to sit in the ground layer, the ground level, it will sit there without any problem. But if you want it to go to the first level, you have to give some energy. Okay? So this is what is called absorption. Absorption means if you send a light with an energy, exactly the energy between two levels, this light will be absorbed and the electron will go to that level. It's exactly like you use some electricity to go from ground to the first floor. Okay? But to come back from there to down, it is easy. You have to just jump. Okay? So when you jump, you release some energy. Okay? This is what happens in atom. Whenever an electron jumps from the higher state to the ground state, it will emit one photon. Whatever is the energy separation between them, that will come as a light. But this is a fixed height. The energy will be fixed. Exactly like the way I said, when you go, only 150 centimeter will go. Okay? So whenever emission happens, because an electron is jumping from one layer to another, it will happen at one wavelength. It cannot happen in all wavelengths. This wavelength is decided by what atom you are dealing with. You understood? So any spectrum, anybody is going to show you, you can now decide in three ways. First thing is that you will just look at whether the spectrum is smoothly distributed. Then you will plot brightness as a function of color, and where the peak comes, you will say this is the temperature. Okay, fine. But then some of you will tell me, no, there I am also finding lines. The lines are coming at particular wavelength. That means lines are coming with particular energy. That means they belong to particular atoms. Okay? So whenever you find the line, you know that there are atoms which are present. In these atoms, like the way we keep going up and down in the lift, okay, we always come back also in the lift, but you can jump also. Okay? In atoms, they jump. They don't come back in the lift. Okay? So this is what is happening. So if you see emission line, what do you mean by that? First thing you will realize is that there are atoms which are present. Second thing you will realize is these atoms, electrons are jumping from top to bottom like that. So I should go slightly fast because I'm going slow like this. So how to make it go up? To make it go up, somebody has to lift. Whenever you are lifting something, there will be absorption. Okay? So if you see absorption, what you know? Something is going from ground to the top. When you see emission, what you know, something is coming from top to the bottom. So this is what is the simple experiments one do. If you look at a star directly, you will find a continuous spectrum. If you look at a star, if you look at a star through gas, because this gas, the starlight can make all the electrons go from ground to the top, because they can push the electrons. This light, when it comes towards you, you will find these photons are missing, because the photon coming from these stars are used to lift these electrons to higher levels. Because of that, they will not be seen. So you will see them in absorption, or if you look at it directly, the electrons which gone up, they will come down and give you emission. So these are the three signals you should see. Of course, I am giving an example. So this tells you if it is hydrogen, you will have these lines. This is laboratory. And neon, you will have these lines. You know which wavelength they have to come. This is for argon. So you know, if you find a line at a particular wavelength, you know whether it is hydrogen, whether it is carbon, whether it is calcium or magnesium. So first thing we learned, two things we learned. We can measure temperature of the star. We can also look at the spectrum to decide whether there are absorption and emission. When you find absorption and emission, you can actually decide how many of them are jumping from top, how many are going from bottom to top. Okay? Then you can also have the composition. What kind of composition they have? Do they have calcium? Do they have sodium? Do they have hydrogen? Okay? Do you have, are you with me till now? Okay, so good. Let's go fast now. Now we are into good mood now. So next experiment we do is to look at the sun. Sun is very whitish in color during the midday. It is red in the early morning or in the evening. Why? Do you remember? Huh? So if you go to a very clean place, will you see red color sun? Absolutely clean place. Huh? You have to think about it. Okay. So this is basically what happens. You are sitting in the surface of Earth somewhere. When the sun is here, sunlight goes through bit of large volume of atmosphere. If you have dust in the atmosphere, what does dust particle do? They scatter the light. They scatter blue light much more compared to the red light. So when you see this one, you will see the red color. Of course, this is why we are using red color for stopping, right? You remember that, because red color gets scattered less. So the idea here is, even though we studied about any object which is emitting high temperature, low temperature, electrons going up and down, there is one more effect you have to worry about. The effect is that star is somewhere, the starlight is going to pass through all the things between us and the star. So you have to experience all the effect we see in real life in this also. So some stars may go through situation like this. They will appear red. Some stars may go through situation like this. They will appear blue. So interesting. Depending upon temperature, the stars can appear blue or red. The same star can appear red or blue depending upon what is the kind of material which is present between us and all. So already I have given you a basic idea between how you can look at, only thing you have to do is that take the light coming from star or any object in the sky and split it into colors. Once you have done that, you will be able to do a lot of things. First of all, you can say how hot it is. Second thing, you can say that how many atoms are excited up and down. And you can also say whether atoms are present in between that object and all, whether they are making it red or blue, in the sense that whether they are dust particle hanging around or there is nothing, pure vacuum. Okay? So this is extremely powerful, right? Whatever I am telling you, it looks very simple, but it's extremely powerful. You have not gone there and you will do this. Okay? So let us see this experiment. Okay, so this I already told you, I will skip. So let's do this experiment, how we are going to probe this. This is the spectrum of sun, this actual spectrum of sun. This yellow color is the spectrum of sun taken outside our atmosphere. Okay? And the red color is the spectrum taken from ground. Why these two things are different? The sun is sun only, na? You understand? This thing should be same, na? Yellow is the, you just go outside our Earth's atmosphere, take the spectrum of the sun. You get this. So what is the difference? Why there is a difference? This place, you see, there is no light coming from sun in this place. Why? Because water molecule in our atmosphere completely absorbs sun's light. The first thing we learned from here is that what kind of composition our atmosphere has. You see, here is the carbon dioxide, water molecules, and you have the oxygen, oxygen 3 molecule, O2 molecule, O3 molecule. So first exercise in studying sun we realized is that sun spectrum will appear different whether you are inside or outside. The difference is mainly caused by atoms which are present in our atmosphere. You are with me? Okay, good. The second thing is that you can now take the solar spectrum which is taken outside and fit it with the curve which I showed you before. Okay? What did we say? We have to see where the peak comes. So look at the peak where it is, and you can calculate the temperature will be around 5300 centigrade. Okay? 5300, which will be 5500 Kelvin. Okay? So that's the kind of temperature. So first thing we learned is that solar light has a temperature which is correspond to 5000 or 6000, whatever you are interested in. So it is the kind of temperature one sees. But now, what I do is that I go and take a small region and make a very good quality spectrum. Means like I am going to divide colors into minute detail and look at how the spectrum looks like of sun. Of course, which you can see even if you go to sunlight, whatever I am going to show. This is what it is. It is blue here and red here. Okay? This spectrum is split and arranged like this for your visualization. What are you seeing now? You are seeing something, these dark lines which are here. Do you see them? So actually, when you look at solar spectrum, people found that there are lines which are present. There are absorption lines which are seen in the spectrum of sun. So what is the idea of absorption lines? Then just now I told you. Is it going from ground floor to first floor or first floor to ground floor? To first floor. Okay. So if you want to produce absorption, means another thing you have to remember is, I am sending photons towards you. There is something in between where all the electrons are sitting in the ground floor. They use this photon to go to the first floor. But these photons, because these photons are used to lift the electron to this thing, they will not come towards you. Understand? So this is why when you find dark lines, means these are the photons which are removed. Why they are removed? They are removed because the atoms use it to go from ground floor to the first floor. So then immediately you are very imaginative people. What is the conclusion you can draw about sun? You can draw interesting conclusion about sun, that is, to produce absorption line, there should be one layer of gas where atoms are sitting in the ground floor, which means the gas has to be cold, because if it is hot, the electrons will go up. If you have lift, you will go up, correct? So this is the idea. So that means the sun, even though we measure temperature of 5500 Kelvin, it cannot be at one temperature. If everything is at one temperature, why there will be absorption? So you should have some region where the photons are created and they are going through a gas where the photons are absorbed by atoms. So this is what given us the idea of what is sun. Based on this kind of analysis, I am giving you one example, but this is not sufficient, you have to do a lot more. What we understood is that sun has a temperature of 5500 Kelvin or 5600 Kelvin. But if I go a little inside, it will be hotter and hotter and hotter and hotter. Because how do you know? Only when you come from hotter region to cooler region, you will be pumping electrons from ground state to the excited state. So this leads us to the interesting aspect that sun is not a body with single temperature, it is a body with multiple temperature. That's the first thing. Second thing is that once you measure the temperature, you will ask an interesting question. See, this is how astronomers ask question. If you just see it, acha hai, nahi hota hai. You have to ask question. Now we know that if I take a balloon or if I take some gas, if I heat it, what will happen to the gas? Heat means it will start spreading. Another example, if I take a balloon and blow air into the balloon, it has a shape. But balloon is so stressed, if I put a small hole, the whole thing will go. The question people started asking, if I take this much gas and keep it at this high temperature, why it is not going away? It should go, na? Gas will just go. Why it is not going away? So this is the question. First they measure temperature. Once you measure temperature, you can say how much force it has to go out. You have done that. Now why it is not going? Sun looks exactly same for us. It looked exactly same 100 years back. What is the problem? So somehow, like the balloon was holding the gas, somehow something should hold this gas together so that it didn't expand to big region. So that is done by what is holding the gas together? Gravity. That's it. So that's what is the model we built. The model we built is that you put the gas, outside gas should be slightly low temperature, so that any radiation coming from inside will go and produce absorption. But you should also have gravity which is holding them in shape. So in technical term, this goes by the name hydrostatic equilibrium. Okay. So we will, so I just give an example. See, just looking at one spectroscopic data, we are able to draw conclusions about what is the structure, and asking one more question, what is the stability, we are able to build the whole picture of sun. Okay, I will stop here because my talk is not on sun. I'm already going a bit slow. We can go further. The next concept I want to introduce is what is known as Doppler shift. See, this is interesting problem. We heard it now. When train comes towards us, the pitch of the sound goes up. Ooh, it goes, right, whistles and all. So what we know is that in astrophysics or in real life, we know that if there is a light source which is emitting light towards you, you detect these lines. Okay. If the source started moving very fast towards you, you will find that the light will move towards the higher energy or lower wavelength. So this has been noticed. This is just a simple effect of relativistic motion, a simple motion. So any object which emits light, if it moves towards you, if it has a red color light, it will appear bluer. Okay. So this is what is known as Doppler effect. Doppler effect means if an object moves towards you, the wavelength will shift towards the bluer side. If the object moves away from you, the wavelength will shift towards the redder side. So this is what is depicted here. So so this shift, object which is moving, what I mean in words, we can explain like this. Suppose this is the spectrum. You imagine these dark lines are the absorption produced by some atom. Okay. If the same region is moving towards you, this is what will happen. Instead of lines being here, they will appear slightly in the lower wavelength side. So that's the thing. So it's interesting for us. So what we have to do is very simple. You take a star. If the star is moving towards you, all the lines will, if the star is stationary with respect to you, all the lines will be in the place where you expect it to be. If the star is moving towards you, the lines will move towards the blue color. If the star is moving away from you, they will go towards the red color. Even if you follow, let's remember this, moving towards us, towards blue, moving away from us towards red. Is that fine? Shall we move on? If you understand this, we can understand a lot of things. Okay. The first thing is related to binary. There are 50% of the stars in our galaxy, they are not single. They usually have a companion. There are two of them going around each other. So imagine something is going around. So when it is here, it will go towards you. When it comes here, it will go away from you. Okay? So this is how it is. So if they produce lines, this is what it is. There are two stars. Okay? So this is the standard line. There are two stars. Because one star is at rest, another star is moving, you will see that when both the stars are rest, they produce lines at the same place. So you should see only one line. When a star comes here and moves towards you, this line will split into two. One is at the same place, another will move towards the blue. When it comes here, it will be again, both are at the same location. So you will have no problem. When it comes here, it is moving towards away from you. So this is very interesting. This star, if you take spectrum, at one point only one line will be there. Afterwards, you will see that another line will appear, which will move like this and join. Next time it will move in the other direction and join. That's what is shown here. You take with single line, it split into two, it becomes single, it split into two, it becomes single. So every time a star go around, you don't see it. Actually, if you go and look at a star, you cannot decide whether there are two stars or only one star is there. You cannot decide. But when you take the spectrum and keep taking it, one time you will find only one line, next time you will find two lines, after some time it will become one line, after it becomes two. So now you can detect binary stars, right? This is the first time we detected binaries. The idea of detecting binaries is that the fact that one is going around the other, we will be able to actually find masses, because this motion is like our Kepler's law, Kepler's motion. The way planets move around Earth, exactly the same physics is applied here. So you can calculate, you can detect whether a star is single or binary through this technique. Of course, this technique can go even further. If you know that you have a very precise way of measuring the wavelength, something else can happen. So imagine there is a star here, a planet is going around. So what planet does? Planet is very small. It doesn't do much to the star. But still, the star will not be in the same place. Star will wobble little like this, because the planet is going around. Like the way, it's not correct, but like the way the waves happen in our sea, that's because of tidal effects. But I'm giving analogous. It's not exactly same. A planet is here, a pull will be towards this way. If it is in the other side, pull will be towards the other way. So what happened? Stars started moving like this. Very little. But if you can detect them, then we can say whether there is a planet going around a star or not. So what principle you are using here? Principle you are using is that there are two principles which you understood today. Absorption or emission line means atoms which are going from ground state to the excited state. Second thing is that that line will come at only one place because it is fixed by which atom you are in. But it can have a small motion depending upon whether the emitting object is moving towards you or it is moving away from you. Okay? If it is stationary, you will find the wavelength something. If it starts moving up and down, you will see this wobble. This is what is shown here. But look at this is meters per second. This is very difficult to do such experiments. So this can be done. So I give an example of how to find binaries. We have given an example of how to find a planet. The next example, which is interesting, this is the galaxy. Now we are going to the slightly different this thing. So what you do is that here is the galaxy. You have seen these galaxies, right? You have looked at them. So you go to different, see this is the center of the galaxy. As you go out, you are going outside the galaxy. So what is shown here is that you go to different locations and take the spectrum. Okay? This galaxy produces some line and you look at the spectrum. The line looks like this. Suppose if you take it as center, this is going towards the higher wavelength and this is going towards the lower wavelength. Okay? So this is this part and this is this part. This part has a spectrum where all the wavelengths are shifted towards higher wavelengths. So what does it mean? If they are shifted towards higher wavelength means that part is going away or towards you? Away, right? And blue means towards. So it's interesting, if the whole thing is stationary, if all stars and all the things are stationary, wherever you take the spectrum, the line should appear at the same wavelength. Okay? This part, the wavelength is more. This part, the wavelength is less. Means what? This is rotating like this. This galaxy is rotating like this. The place when it is coming towards you, you will find blue. This part will be red. Here what happened? This part is going out. It is rotating like this, right? Imagine like this. So first thing we realized is that by doing the spectroscopy and with simple idea of Doppler, we can now say galaxies are rotating. Correct? So that is the first thing. So you understand, it's interesting. We say they are. So you will ask, what is making them rotate? Okay, that's a good question to ask. So let's see how it should be. So again, what happened? Ideally, if you think of rotations which are happening, if you take one star, the star is rotating because of what? Because of all the gravitational force coming from the galaxy. All the mass and what is the distance, that will decide what is the speed at which the star will rotate. Okay? Interesting thing is that people actually plot distance from the center, what is the velocity, how velocity changes, how the speed changes as you move from distance to the outside. People found that this is how it is changing. The red color is the observed distribution of velocity. You understood, na? How much, if it is shifting in one way, we can calculate, na, velocity. What is the velocity at which it is shifting? But what one predicts, suppose you say that all the mass in this galaxy are residing in stars which we see, the stars which you are seeing have all the mass, then you can calculate what should be the speed at which different stars should move. That is like this. If you apply law given by Newton and take all the stars and calculate mass of the stars and expect how the objects should move as a function of distance, this is what is expected, and what you are observing is this one. So what do? They are not same. There are two options for you. First option is to say Newton is wrong. It's very easy to say. But he cannot be wrong. All ISRO satellites are going to the correct place because Newton is correct, right? The alternate explanation is, in a galaxy, the mass is not only in stars. There are huge amount of mass which is invisible. So this is the idea of what is known as dark matter. Okay? So dark matter was needed just to explain the way stars are moving around this thing. So I am going extremely slow. Can I take 10 more extra minutes or something? Otherwise I will not finish any of this. The same exercise you can do closer to the center of a galaxy. Close to the center of the galaxy, you take the spectrum of gas which is there and look at blue, and again it is like this. So this is one of these M83 galaxy. You go and take a small region and start looking at how they are moving, and you see that stars are moving violently. One part is moving towards you, another part is moving away from you very rapidly. This amount of rotation one sees in the center of galaxy is much, much higher than what you can see outside the galaxy. Then people want to figure out what is there. So then they said there are black holes. This is the way people found that in centers of every galaxy there is supermassive black hole, which makes object go very fast. Is it true? One of the real direct example is in centers of our galaxy, where you can look at each star and keep taking photograph and see how they are moving as a function of time. In our galaxy, we can see these stars, and then one can actually come to conclusion that even these stars, they are moving under the influence of gravitational potential of a gravity of a super compact massive object, which we call black holes. So I just introduce you simple things: how to detect planets, how are we detecting dark matter. Now we say we are detecting black hole, all with only one simple idea. Lines are created from atoms. The wavelengths are related to the motion, okay? Infall and outflow. So now at least you should know, when somebody asks how black holes are detected, how dark matter is detected, you have some idea, okay? Let me just go quickly into this. Okay, the other thing one can do with the spectrum, which I already said, so I can move fast. You can look at the lines. The wavelength at which lines are coming, you will know that which element is creating that line. Suppose if I go and look at the spectrum of a star, which has line coming from only hydrogen atom, what will be my conclusion? The star has only hydrogen. If I have a star which is also producing absorption lines of carbon, nitrogen, whatever you can think of, sodium, magnesium, zinc, chromium, then you know that this, so you can actually do the composition, and studying composition is another topic which is one of my favorite topics. This is what I work on, it's like chemist, to understand how these elements are created, how they are distributed, etc. So I will just leave you from here. We will not go into this I already explained to you. So in some regions, if you look at, you find these dark patches. In some region, you take images, you see dark patches. There are two options of this. One option is that somebody went there and cleaned up all the stars, so that there are no stars there. Another option is that star is there is a monster cloud in front, which is removing all the light, like the way it happens early morning and evening in our Earth's atmosphere. Earth's atmosphere is like that. That means things should look red. So in the same region, if I go and make a deep image in red color, I should see them. That's what is here. If you go and do the deep images in red color, you see the stars there. So this is another thing which we talked about, which is what is known as dust. So dust is another important thing which has a important consequence to us, because understanding how gases are there is easy to understand in astrophysics. But how to form dust means a solid particle. That means you are making different atoms to join into form some structures. So this is very difficult. So detecting these things in space is very exciting, and then one can understand how these structures are created. Consequence of this is that these structures in a complex situation is what will lead to our life. For example, you know, benzene, our biological sequences can start from simple structures like benzenes and what is known as aromatic hydrocarbons, which are simple structures, biological structures, or you can think of like graphites and silicates. These are like layers of solid structures. Detecting them is very interesting. In fact, you can detect with spectroscopy. This is what is example I am showing here. These are emission which are seen in some of these stars, and this can be used to actually say at what kind of temperatures and what kind of composition one can have these structures, because this is very important building block. At least you have to form them before forming life. Okay, so that's okay. I'll just go quickly now into a couple of the slides. So actually, spectra of galaxies are also very different. If you take an elliptical galaxy, the spectrum will look something like this. There will be no emission lines which are clearly visible, whereas if you go to the spiral or irregular galaxies, you will start seeing emission lines. So spectrum actually changes depending upon what kind of light and what kind of composition of galaxies which are there. So like the way I explained to you about stars, one can also look at each features in the spectrum and decide what kind of galaxy it is, what kind of objects it is possessing. So I have two more things to explain to you, and afterwards we will finish my lecture. Okay. The first thing is related to what is done by Hubble. So what Hubble did, this is the last experiment related to the velocities. So we have found these velocities of moving thing. Now we use this to find binaries, we use it to find planets, we use it to say dark matter, we use it to find black holes. The last thing, one of the applications at the largest distance is to understand about our own universe. What Hubble did was, he looked at galaxies at different distances. These are the distances given, and he considered similar set of lines. Okay. What he found was, when you look at galaxies which are further and further and further away, the lines are shifted more and more towards red direction. So it was puzzling. So what is the conclusion? Red means these galaxies are going away from us. Correct? Going away from us. And further the galaxy, it is moving faster. Okay. So what could be the reason? Because all galaxies don't like us. Right? The other possibility is that we are the center of the universe, because everything is going away from us. So usually it is good for politicians and human beings to like this way. I am the great guy. I am the center of this thing. Physicists won't like that. If you find one special place, one special thing, that means there is problem. We would like to generalize everything, right? So how do you understand this? So this is an important finding by Hubble. Hubble found that objects appear to move faster when they are farther from us. It is called appear to move. Okay. So appear to move means velocity. So we have to understand what is the velocity. So the basic idea behind is something like this. Okay, I think this slide is okay. I will give you an example of simple example of what is the velocity. How do you mean? So I keep my two fingers like this. I move here. Can you calculate what is the velocity at which I moved? You can, na? You take your stop clock, start it, and find out how much I moved, and you have a scale which tells me how much I am moving. So you can calculate velocity, correct? So if velocity is given, it will decide whether to go blue or red by what amount. But I have a slightly different experiment. I am keeping my two fingers. I also fix my scale with my finger. The scale is a rubber. Okay? So I do like this. This time I find 1 meter, suppose. And you start your stop clock. I move like this. So you think distance is increased. I look at my scale, it says 1 meter. It doesn't change at all. Because the scale I am using is rubber, which is also moving with me. Okay? So if you ask me what is the velocity, I will say 0, because nothing has changed. You are saying what you will see. You will see something has changed. So this is exactly what happens in an expanding universe. This is the example shown here. You take a balloon. Don't look at the squares. Just look at this sine wave which is there. This balloon has become bigger. Wavelength can be measured between two peaks, right? Going from one peak to another peak, or one trough to another trough will give you wavelength. Okay. Now tell me what happened here. Is it same? This curve looks same or different? Different, right? But if I put the grid, with respect to the grid, is it changed? No. So this is what precisely you have to remember. the way the wavelength change occur in universe was understood by saying that universe is expanding and we are frozen in that. The wavelengths are frozen in that universe, right? Imagine whatever photons we are creating, they are in the universe. When the universe expands, in that frame, like the scale we said, nothing is changing. So a universe was smaller in the past. Suppose imagine universe was smaller in the past and it has become bigger now. The anything which was smaller there would have appeared bigger today. You understand? So this is what is known as cosmological redshift. This is a very deep idea. So you don't say, there are for two reasons when we are looking at the results of Hubble, we never said that galaxies are going away from us at higher speed. One reason is whatever I said, physicists would like to not make us special. Second thing is that to move a car at 50 km per hour, how much work you have to do? है ना? Car के इतना. Can you make a sun move? Now it is stable. Na? If it wants to move with 1 km per hour, will it be possible? But you want to make it move very high speed. Is it possible? No. Because energetically, these are not possible. Okay? This is why people thought about it. And this led to an interesting consequence saying that the galaxies which are far away, now you see, I am going to connect to whatever we said before. Galaxies which are far away, I am looking at it today, that light would have started long time back. Okay? When the light has started long time back, the universe was smaller. It took so much time for light to travel from there to me. By the time it reached to me, the universe has become bigger. Same experiment like this, what I did. Okay? So the amount of shift you see, suppose a line is shifted by some amount, it is not reflecting the speed at which the galaxy is moving. Rather, it is telling what was the size of the universe when the photon started from that point and today, relative size. If the size has changed by factor 2, the wavelength will change by factor 2. Actually 2 plus 1, 3 times. Okay? So this scaling one can do. So now you understood, na? The way we are going to understand the Hubble constant is that the galaxies appear to move away from us. Further the galaxy, the time taken for light to come from there to us is larger. Moving away is nothing but wavelength being stretched. So if light takes a lot of time to travel, it is traveling from a smaller universe into a bigger universe. Universe is also changing. Okay? This is the basic, is my experiment like, I am changing, my scale is also changing, so I don't see anything, but you are seeing it because you are sitting there. You are not evolving. So I hope this gives you an idea. This is what is used to do whatever we call, understand the cosmology. That means larger shift of wavelengths, that means you are picking galaxies from further and further and further and further away. So it is the very interesting concept. This is what you use to build the whole history of the universe. Starting from very small universe, you can build. So if you are interested, probably when you are around, if you end up staying in science, and if you are in Masters or BSc, you should come and attend summer school or visiting students program at IUCAA, where you will learn all these things thoroughly. How, because now it may appear magic, but you can start deriving from scratch and get whatever concept I am telling in a hand-waving way. Okay, last bit I wanted to say is that if you go to very distant universe, you see that we talk about stars and we talk about galaxies, but it is also interesting that lot of things are in between these galaxies. How do you know it is there? This is done with these experiments. Whenever you look at a distant star, actually I move an object called quasars. Quasars can be seen to very large distances. When you look at these quasars, you see that their spectrum is filled with huge amount of absorption lines. The idea behind is that this tells you that not only matter, see we talked about dark matter. Similarly, we can also identify that when you look at very distant object, when the light coming from that distant object towards you, it picks up lot of signals in the medium in between us and that one. So I just have a small movie to show you. I hope it runs. After that, we'll stop. So you see that blue color is the photon, which is coming. When it moves, you see that you will start seeing signatures because of whatever is present here. There is a galaxy through which it will go at some stage, but it depicts that even between galaxies, in between galaxies, there are a lot of gas. And this gas plays an important role in deciding our universe itself. This goes by the name intergalactic matter. nearly 80% of the matter is present there. Okay. Now, when it goes through the galaxy, you will start seeing a big absorption line produced by the galaxy and lot of other signals which are created. So, I am just giving you a simulation of whatever one can think of. The idea here is that first we talked about emission, absorption, property of the gas, motion. We can also use imprints of material in between to study a lot of things. Okay. The analogy of this is bit like the way Americans caught Bin Laden. They didn't look at Bin Laden directly. They didn't have any information. They went and looked at the dustbin there, and they figured out that there is some activity going on. Medicine is going on. This is there, right? And also, if what is that? COVID was there. Amount of COVID spread was detected based on what is there in our what is that called? Sewage water. So they analyze by analyzing this. Exactly like this, what is happening in the whole universe, you don't have to look at all galaxies. You can look at what happens in the material. These are like dump yards. You can look at these things and you can develop a lot of insight into this. This is again, this is one of the key research areas in IUCAA where people do this. Okay, I will finish with some positive notes. These kind of things, exercise, if you want to do, you need to do it with very large telescopes. We cannot do it with small telescopes because the objects which you are detecting cannot be seen with our eye. They are billions of times fainter than what we can detect with our eye. So now India is investing in couple of big projects. One is what is known as 30-meter telescope, which is going to be in Hawaii, which is India will have 10%. So when you become astronomers, unlike me, you don't have to worry about where will I get my next data. You have right to go to the biggest telescope in the world available to our country. This is major development which has happened in last 10 years. Similarly, we are all used to GMRT. So if you imagine going to 20 times the GMRT or maybe 50 times the GMRT potential, that is what is going to be square kilometer array. This is again we are part of, and you will have direct access to taking data. This is not possible now. World's biggest telescope, Indians have no direct access. So we have one telescope for which IUCAA has little bit access, but this is not the most sophisticated telescope one can think of. The situation will completely different in next decade, where you will have direct access to all these things. Okay, so of course, this is what I want to say. I will stop here.
I've made a lot of videos, but a recent one somehow engaged many viewers. This video was about why light slows down when it enters water, glass, or any transparent medium. For some reason, this video took off and the comments were very interesting, covering the entire gamut of claiming that the video was insightful to claiming that it was utter rubbish. But one particular question appeared over and over again, and that comment was, but why does light bend when it goes from air to glass? And it's true that I didn't answer that question because, well, it wasn't what the video was about. But a lot of people ask, so in this video, I thought I'd tell you why. Now, as it happens, there are lots of wrong explanations out there, lots. So the first thing I'm going to do is tell you the wrong ones and why they're wrong. Don't be surprised if I debunk one you learned. So let's start with what we see when a beam of light hits glass. Light traveling through air will change its direction when it hits the surface. The amount that its direction will change depends on the angle at which it hits the surface. Change the incident angle, and the transmitted angle will change correspondingly. Those angles are related through a physics formula called Snell's law, named after Dutch astronomer Willibord Snellius, who lived in the 1600s. I have his formula written over here. If you'd like to learn how to use the formula, there are many online tutorials, but I'm not going to cover that here because I want to get into the question of what is the physical process that causes the path of light to change as it enters the glass. So let's get into it. There are three commonly suggested explanations that are wrong, or at least incomplete. They are Fermat's principle, the analogy of soldiers marching, and Huygens' principle. Fermat's principle says that light will travel from one point to the other, taking the minimum amount of time. It's often explained in terms of a lifeguard and a drowning swimmer. In order to maximize the chances that the swimmer will be saved, the lifeguard needs to get to them as soon as possible. So what path does the lifeguard take? He could run directly to the water and start swimming. This means he would swim a long distance, but because he can run so much faster than he can swim, that'd be a bad choice. So you'd think that he might just run over to the point where the swimming portion is shortest, but that turns out not to be the shortest time either. Then there's the straight line path, and because the shortest distance between 2 points is a straight line, you might think that this is the fastest path. But because swimming is slower, it still isn't the shortest time. It turns out that the shortest total time, that is to say when you add both running and swimming time, is exactly what you get from Snell's law for light. You run a little longer than you would for the straightest path, but that means that you swim a little less and the total time is shortest. And that's exactly what light does. It follows the path of shortest time. But while that's true, it doesn't explain anything. It just says what it does, not why it does it. So that's not an explanation, and we need to come up with a proper reason. Let's look at the second option on the list. A very common explanation used to teach why light bends involves soldiers marching over firm ground, but then who encounter mud, although not all soldiers hit mud at the same time. The idea is simple. The first soldier who encounters the mud cannot move as quickly as the rest of the soldiers, so he slows down. Each soldier hits the mud in turn, resulting in a direction change. Eventually, the lines of soldiers are moving in a different direction at a different speed. This is how it's often taught. The problem is that this doesn't work. In fact, the soldiers will slow down, but their direction doesn't change. They will continue to walk in the same direction, but with marching lines that are slanted compared to how they started. This explanation gets the angle of the lines of soldiers right, but not the direction of travel. In fact, the only way that this explanation can be right is if the lines of soldiers are rigid. Then, the first soldier hitting the mud puts a torque on the entire line, and that would work. The problem is that this torque means that the soldiers on the top of the screen move faster, which is to say that if they were light, this part of the beam of light would have to move faster than light. So this explanation doesn't work either. Okay, so far we have a non-explanation and a wrong explanation. What about Huygens' principle? Huygens' principle, named after Dutch physicist Christian Huygens, depends crucially on the wave nature of light. We know that when a wave encounters a small gap, the wave passes through the gap and spreads out. This principle is called diffraction, and it's universal to all waves. If waves hit more than one gap, each gap will allow waves to pass through and make ringlets. The waves from each gap can interfere with one another, with the waves either adding to or subtracting from one another. In this animation, the lines show the position of the peak of the waves. Showing how the waves add together is perhaps easier looking at them from the side. When the peak of two waves encounter one another, the result is a single and bigger wave. And when a peak of one wave hits the trough of another wave, they can cancel each other out entirely. What Huygens claimed is that there is no need for gaps. Each and every spot on a wave was acting like it went through a gap and was spreading out. Now we can take that idea and have waves moving in one medium transition to another medium where the speed is different. So we can take light traveling through air and shoot it through glass. And because we're interested in explaining the bending behavior, we'll have light hit it at an angle. Here's how the Huygens explanation goes. What happens is that the wave peaks hit the glass at different times. The waves then spread out and begin to interfere with one another. Notice that the wavelength is shorter in glass. That's because the wave is moving more slowly. Where the lines accumulate, that's where the waves add to one another. And they don't just line up in one spot. They line up again and again. Remember that the lines denote the top of the peaks of the waves. We can see that there are many places where the peaks line up. We can overlay a couple of lines that show the direction that the wave is traveling and then remove the circular waves, and we see that this explanation seems to be doing a good job of predicting what happens when light goes from air to glass. Looks good, right? But not so fast. What happens when we look at all of the waves coming through the glass? Things get a lot more complicated. We do see that the waves add together to predict the direction that light moves in glass. On the other hand, that's not the only alignment. For instance, we see other geometries where the waves line up. There are the wave fronts that are going this way, and then there are the wave fronts going this way. So that's a problem. It seems that this approach doesn't give a unique prediction. Okay, we've ruled out Fermat's principle, the soldier analogy, and Huygens' principle. These are all often seen as explanations of the cause of refraction given by people who really do know some physics. So what's the real answer? It turns out that the only way to really answer the question of why light bends when it goes from air to glass is to get serious about the nature of light and to embrace the fact that it is made of oscillating electromagnetic fields, and that means you need Maxwell's equations. Because this isn't a full-blown physics class, I'm going to focus only on the electric fields. And I'm not going to do the derivation because that's the fun part. I'll leave that to you. But the big ideas are actually pretty straightforward. You start with Maxwell's equations, which are always beautiful to see. They're a little scary looking, but the question we're trying to answer is an easy one, which makes the whole thing a lot simpler than you'd imagine. In fact, we're going to need only the bottom two equations. So let's see what's going on. We start with light going from air to glass, hitting the surface at an angle. In our figure, we can replace the waves with the direction of motion. Now it turns out that the electric field of light is perpendicular to the direction that light is traveling, and we can add that field direction to the diagram. And it's very important to remember that this field has a component both parallel to the surface of the glass and one that is perpendicular to the glass. And here is where Maxwell's equations come into play. Two copies of the equations are written here, one that covers when light is traveling in air and one where it is traveling in glass. So here's the key point. The surface belongs to both the air region and the glass region. This means that at the surface, the equations on the top and the equations on the bottom have to apply. And with that little bit of calculus, you can find two important restrictions. The first is that the electric field parallel to the surface of the glass has to be the same in the air and the glass. And similarly, perpendicular to the surface, what has to be the same is the electric field times this epsilon, which is different for each material and depends on its molecular makeup. We can then manipulate these equations to see what the electric field in glass should look like. Because epsilon is bigger in glass than in air, that means that the perpendicular electric field in glass has to be smaller than it is in air. Now we remember that the direction the light travels is perpendicular to the electric field, so we can put in an arrow to show the direction light must travel in the glass. And finally, we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air. Okay, what I just showed you is an equation thing. You're probably asking yourself what that epsilon actually physically means. It's there because of how the electric fields from the light interacts with the matter in the glass. You start out with glass with no electric field in it. The glass has charges in it, but they're arranged in a random way. But when you send light in, you impose an electric field on it. That field makes the charges move around, which sets up a counterbalancing electric field from the charges. The result is that the electric field in the glass is lower than it is in air because of how the electric field from the glass is in the opposite direction. And this is the reason that the perpendicular electric field is lower in glass. And that, my friends, is why light bends when it goes from air to glass. It's not because of many of the ordinary explanations. It's because of how light interacts with glass and changes the glass's properties. And it's because the electric field inside the glass is affected by the arrangements of atoms and molecules in the glass when light hits it. It's the same reason why light slows down in matter. Inside matter, the electric field due to the light and the electric field due to the matter both have to be taken into account. Outside, they don't. And now, you know some serious physics. Okay, so that was a very long video. It kind of had to be to cover the many incomplete or wrong explanations and then explain the correct cause. And I imagine that some of you will ask about the quantum explanation, which is similar to the one I told you here using Maxwell equations, except using energy and momentum of the photons instead. There's always more to learn in physics, always more. And you knew that because, of course, physics is everything.
Now we'll close with the merging of two neutron stars. This footage was produced by the Pleiades supercomputer at NASA's Ames facility, and it shows a simulation of two neutron stars colliding. When they do, you'll notice that it gives off ripples of gravitational waves, and depending on the size of the neutron stars to begin with, it'll either form a bigger neutron star at the end of it or a black hole. And either way, they'll give out a gamma ray burst of energy. And interestingly, the calculations show that that gamma ray burst of energy, if it's pointed towards you, it'll kill all life within 33 light years of it. So you don't want two of these things merging anywhere near you, because 33 light years is quite a big distance. And a neutron star is typically 10 kilometres across, maybe up to 20 kilometres across, so it's very small, and one half or more suns of mass in it as well. So fairly light in the bigger scheme of things, but it gives off an awful lot of energy when the two merge. Magnetic field's about 1 trillion times more than here on Earth, so it'd rip matter apart that was anywhere near it. And with that, I'll close the meeting, and hopefully we'll see you all at the August meeting. Thanks for persevering.